All right, and welcome to the chapter 7, new chapter here on quadrilaterals and other polygons. Mainly focus on quadrilaterals, but this first lesson here we'll go over some basics that apply to all polynomial, or I'm sorry, all not polynomials, all polygons. Holy cow! So we'll kind of crank out this first big idea for the chapter: interior and exterior angle measures of polygons today, and then most of the rest of the chapter 7, 2, 3, 4, and 5 all focus on specific types of parallelograms or other types of quadrilaterals, rhombus, kite, stuff like that, trapezoid. So stuff you may have heard of, but we'll get into some of their properties and use them to help us find unknown measures and lengths and angles. And so let's jump in today, specifically 7.1. Like I said earlier, angles of polygons. We'll look at interior, exterior angles, angle measures, and yeah, that's pretty much it. So here we go. First thing, a vocab word. Make sure we add this to our notes. Pause it. Diagonals, or what we wrote in class as diagonal of a polygon, as like the vocab term, and it's essentially the segment or a segment. There's a lot of them that connect two non-consecutive vertices. Okay, so obviously on this the picture that's here, we've got polygon A, B, C, D, E. Just a quick refresher. That's how you name a polygon. You just use the vertices in order. Could be counterclockwise, clockwise. Don't have to start alphabetical or anything like that. But so polygon A, B, C, D, E, the big, what we would call a five-sided a pentagon. And all that's really going on here is we've drawn two of the diagonals. So from B to E, B to D. But obviously, like we said, we could go from C to A, there's another diagonal. C to E, there's another diagonal. You could go from, what don't we have yet? D to A. So there we go. We end up, we could, and I'm sure that's maybe something you've done. You've just kind of doodling. Even sometimes you'll sketch stuff like that. But so those are all the diagonals in there. We want to just focus on these two here because it leads to kind of what we're talking about today. So if I just highlight BE and BD, those are two of the diagonals in this polygon. And just I'm kind of summarizing here. When we focus on just one vertex, drawing or sketching the diagonals, we end up dividing the polygon into a couple different triangles, 3 different triangles in this case because it was a 5-sided figure. The way it's going to work out all the time, basically, however many sides we have, if it was a 10-sided figure and I kind of followed the same process and drew all my diagonals, I'd divide the triangle into divide the polygon into 8 triangles. Basically, you're always going to be too short from the sides because if you look, if I were to try to draw from that's why this definition of non-consecutive, or where this comes into play here, B to A and B to C aren't diagonals, right? Those are just the sides of the polygon. So, yeah, we always end up with 2 shorter or 2 less triangles than we have side lengths. And ultimately, where this is all leading in, and you can kind of, if you're following along, see that each one of these triangles, we know from previous chapters, the interior angle measures add up to 180, 180, and 180, which was covered again in 2 chapters ago. The sum of the whole figure, the pentagon in this case, should be 180 plus 180 plus 180, or 180 times 3. Yeah, kind of putting those two concepts together: the number of triangles and the fact that a triangle interior angles measures are 180 leads us to kind of the one of the big formulas for the day. So in class, we set it up as we put the polygon interior angles theorem. We use this abbreviation here, so capital S with a little, it's still a capital, but a subscript I, to stand for the sum of the measures of the interior angles of a convex n-gon. Like, it's a lot to write, and obviously I don't want to have to write that every time. So this little SI that I'm writing right here is meant to stand for the sum of the measures of an interior, so sum of interior angle measures, basically, is equal to essentially what we just talked about, the number of sides, so that's what n stands for, minus 2. So take away the, accounting for the fact that we can't, we're always going to be 2 short triangles. So this is going to kind of tell us how many triangles we're dividing into, and multiplying that number times 180 degrees. So I'm I'm essentially restating right here. That's the formula that we're going to use for the sum of interior angles of a convex n-gon. All right. We ended up not adding this. Remember, a corollary is just something that can easily be proved from another theorem. I hope everybody's comfortable with the fact that triangles, interior angles add up to 180. I think you either knew maybe even before we started the lesson, or if you don't, you'll see it so often that the interior angles of a quadrilateral is 360. But that really stems from, this same, hey, 4 minus 2, quadrilateral is 4 sides, 4 minus 2 times 180. 4 minus 2 is 2, 2 times 180 is 360. So that's where it's coming from. I don't think it's worth necessarily adding to our notes. We'll come to know this, I think, throughout just the kind of the course, the nature of how we do things, that you'll know that without having to write that down. Okay, so let's look at a couple examples really involving this sum of interior angles. Okay, what do some of the questions look like? So one way that we could potentially use it is, the question is asking us to find the sum of the measures of the interior angles of a convex dodecagon. So, kind of picking the problem apart here, pause, try it, write it down, give it a shot, and then here's the solution. I want to use that formula, right? Because what is the S? What did we say the little SI stands for? The sum of the measures of the interior angles of a convex, right? So that's what we want to use there. The one that makes this one tougher, or instead of just saying, here, use this for number of sides, because obviously that's pretty easy, just to plug a number in for n. I'll write the generic formula here, n minus 2 times 180. That's the formula we should be using. But obviously, if we don't know n, I can't really use it. So what is dodecagon? This whole question kind of boils down to, what is dodecagon? And hopefully, we flip back. Lesson 1.4 is where I think we originally took these notes. That's a 12-sided polygon. So that's kind of the magic number that I need to use here. So as I substitute in here 12 sides minus 2 times 180, and that ends up being actually a relatively doable, like in our head type of calculation. The sum of interior angles of a convex dodecagon would be 1,800 degrees. So I think a pretty straightforward use of the formula, kind of hinged on us knowing that dodecagon means 12. So go back, refresh some of that stuff as well. Like I said, lesson 1.4, where we covered some of the polygon names 3 through 12. All right, let's look at another example. Okay, it's a slightly different, a little bit different twist here on this. So again, write it down, read it yourself first, pause it, try it, and then come back here and check the solution, which is right here. So it's asking us the sum, or it's telling us actually the sum of the measures of interior angles of a convex polygon. So it's a lot of setup, a lot of verbiage there, but it's all saying the same thing. The sum of the measures of interior angles of a convex polygon is 1,260 degrees. It's asking us to classify the polygon by the number of sides. So it's almost like it actually is. It's a true reverse of the problem that we just looked at. So it's still that same terminology, sum of the measures of interior angles of a convex polygon. That's our SI, right? So there's kind of a trigger there saying, hey, the sum of interior angles, where's that formula? N minus 2 times 180. If I want, obviously I think there's people that can guess and check and figure this out, just kind of playing around with their calculator. I kind of want to take that out of it and just make it more concrete. So I would look here at something like, okay, well, there's the formula. What do we know? Where does this 1260 go? That's obviously not the number of sides. It's asking us essentially to figure out how many sides there are. So what would I do? I replace the sum of interior. It tells it is 1260 equals 1260. So the 1260 has to go here. I've got my n minus 2 times 180. And then we'll use our algebra skills to solve for n. So hopefully we'll be able to solve that. I'll run through it. You could distribute probably more work than we need to do. I would look at, right off the bat, at this point, dividing both sides by 180. To get it out of this side. 1260 divided by 180 is 7. Really common mistake is to say, 7 sides, done. Obviously, there's still going on this right side of the equation. There's this n minus 2, so to algebraically move that minus 2 or get rid of it on the right side, I need to add 2 to both sides. So we'll end up with n equals 9, 7 plus 2. And even that, I'm not wrong, but I didn't really answer the question or do what the problem was asking me to do. It said classify the polygon by that by the number of sides. So I still have to go back and look at refresh from lesson 1.4. A 9-sided figure we do call nonagon. So in the end, that's what we're looking for. I mean, are you losing all your points if you say 9? No, half point here, there, whatever. But we should say in the end a nonagon. All right, one last one, kind of using the interior angle formula. Yeah, just a little bit different twist here on it. A Mr. Kroll classic homemade figure here. So find the value of x in the diagram shown. So if you can't tell, this is one that I put together here. Find x, right? So I see a couple different x's. I got 2x showing up here. So that must mean this angle and this angle are the same. Don't necessarily trust my numbers here. I don't think for accuracy, I kind of just put numbers in there to make it somewhat make sense. Hopefully it works out here in the end. So a couple different things. What makes this one different? Well, we don't know the sum, right? I don't know what these all add up to. I've got a couple different x's. And I don't even know how many sides. Ultimately, I can count in this one and figure out how many sides. One thing you can do too, and I don't know if we explicitly said it earlier, but the number of angles of interior angles should be the same as the number of sides. So sometimes it's easier, almost I would say, to count angles than it is sides. Although you could use little dots or tick marks to say, okay, I'm going to start here. It's easy to double count or miscount. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 10 sides. I should have. Make sure you account for all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I got 10 interior angles. So different ways to start this problem. I think the one thing we need to know at some point is what should all these numbers add up to. So the sum of interior angles, I won't rewrite the whole formula again, but if it's a 10-sided figure, I'm going to have to do 10 minus 2 times 180. And let's just, I've got my calculator here in front of me. It's going to be 10 minus 2, which is 8. 8 times 180 is 1,440. So when it's all said and done, I think that's a number that we have to calculate at some point. 1,440 is what all these should add up to. Okay. And then I've got, so I guess we want to start to set up an algebra problem, 1440. And then when I add all these numbers together, and I do have to do it, I don't have it written down, I'm doing it right with you. I've got 151 plus 168 plus 120. I just don't want to miss one, so you can kind of see I'm highlighting and I'm underlining. You should be doing the same stuff, plus 141. Now I'm talking, of course, I'm going to miss something. 133 plus 111 plus 164 plus 130. When I add all those numbers up, I get a 1,118. Okay. Now I'm not done because obviously I've got this 2x and this 2x to account for. There's two of them, so hopefully you're okay with me just saying, hey, 2x plus 2x is 4x. So I'm left with, all right, on the left side here, my 1118 plus whatever 4x comes out to be needs to come to a total of 1440. All right, so we've got a relatively decent a two-step solve here, so we'll subtract. I won't show every single step, but I'm going to subtract. Let's see, 1440 minus 1118. I'm getting 4x equals 322. Divide both sides by 4 to get x equals, oh, not terrible, 80.5. Now, that's not degrees. That's what x is equal. We could plug it back in and figure out what each of those angle measures are. But yeah, I guess one other just instance of kind of putting it all together, saying, hey, I find the sum, using some of those algebra skills, making sure we don't miss anything, add them all up. So different look for us. So there we go. There's a couple different ways using that sum of interior angle formula. We'll come back to it actually and revisit it here at the end. Or actually not we're getting towards the end. We'll revisit here shortly. So switching gears a little bit from sum of interior angles, just a quick vocab for everyone. So pause it here, add these to your notes, 3 terms that we added in class. The first 2 we should totally be familiar with from previous lesson. We talked about an equilateral triangle and an equiangular triangle. They were one and the same. So we have the same thing going on with polygons. We could have an equilateral where all sides are congruent. We could have an equiangular polygon where all the angles are congruent. But what the difference here is, remember, like I just said a second ago, with a triangle, it was if I knew one, right, equilateral, also just had to be, I know it's perfect color to be using right there, had to be equiangular. Like that, one led to the other, vice versa. If I knew something was equiangular, it had to be equilateral. So we're seeing with other polygons, though, you can have a hexagon that's equilateral but not equiangular. You can have a hexagon that's equiangular and not equilateral. When those happen to come together, when these 2 concepts come together, you can see it right here. It's called a regular polygon, which is a little bit weird, almost like counterintuitive. It's, just a regular old polygon, just regular. But it's actually regular is super specific, saying that, hey, that when I see that word regular, I need to know or understand that that's talking about, hey, okay, that's equilateral and equiangular. So regular means equilateral and equiangular. So just kind of an isolated vocab concept there for us. Last notes section that we'll need, and then we'll do a couple examples, focuses on exterior angle measures. Okay. So we'll do the kind of the same thing that we did there, is get up a heading on your notes, exterior angles, using exterior angles. So I like the picture actually here. It kind of illustrates, I think, exactly what we want to talk about here. So we're still talking about the sum when we, adding up exterior angles. But what's kind of cool, I think it's at least unique, or it's somewhat interesting in the fact that it doesn't matter how many sides you have. You could have a 500-sided figure, which obviously the sum of those interior angles would be crazy huge. 500 minus 2 times 180, huge number. The exterior angle sum never changes. Okay, so like I said, I think it's kind of cool with the colors, how it matches up here as far as you got to have a little faith that, all right, remember exterior angles, just as a review, forms a linear pair with the interior angles. So we did something in class just as like a quick review to say, like, if this is a polygon, remember my exterior angles would be forming a linear pair. So an interior and exterior angle measures sum would add up to 180 degrees. So you can kind of see it's the same thing. You have an exterior angle for each interior. It's a 5-sided figure. I've got 5 exterior angles, and we kind of pull each one of those apart and keep them in the same position. We're able to put them all together, and there's the big reveal. I know it's been on the screen the whole time, but 360 for any sided polygon. So that's kind of cool that there's not actually a formula. So this kind of leads to what we took in class. We said the polygon exterior angles theorem that says the sum of exterior. So same, we don't have to write the whole thing. I guess it's this right here, the sum of the measures of the exterior angles of a convex polygon, right? We're abbreviating with SE, little subscript E. It's not even a formula. It's more like a fact, a statement, is equal to 360. Right, so let's use that example. So for a 500 gon, holy cow, 500 sides. There's no way you could draw that. But a 500 gon for the interior angles, that's a little bit of a calculation. 500 minus 2 times 180. Is this going to overload my calculator? I don't know. Probably not. 498 times 180. Oh, the sum of the interior angles add up to 89,640 degrees. Huge. Like each one of those angles are going to be like almost a linear, like almost a straight line. Like they're so obtuse that, I can't sketch at 500 sides, but without doing a single calculation on that 500 gon, I know that the sum of the exterior angles is 360 degrees. And hopefully that kind of makes sense. Just think about it. As the interior angles get bigger and bigger, what's happening to that exterior angle? It's getting smaller and smaller. So you're going to have 500 exterior angles, but actually they're all going to end up being less than 360 degrees. So, well, not all of them necessarily, but, or I'm sorry, all less than 1 degree each. Anyways, so that's the big takeaway there. I think I misspoke a second ago, but sum of exterior angles, doesn't matter how many sides you have, always going to be 360 degrees. So we look here, 2 examples left using that same concept. The figure kind of stands out. It's kind of cool looking, like a pinwheel almost. They all look to be exterior angles. Boom, 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 boom. Similar to the one we did here with the decagon. Find the value of x, saying, okay, we can do that. What makes this problem, I think, a little bit easier is I already know I don't have a single calculation to do just to know that, hey, these all have to add up. This one, this one, this one, this one, this one, and this one all have to add up to 360. So I'm going to do that same thing. I already underlined it, but 62 plus 35 plus 69 plus 41 plus 58 plus 5x. So let's, whoops, oh darn it, I had an extra plus on there that I didn't mean to have. 265. So the actual number values all came together to be 265. But then when I add that with my 5x, we need to get to 360. Okay, so we'll do a quick 360 minus 265. So 5x has to be equal to 95. We'll divide both sides by 5 to get x equals 19. And I think we're okay. We could double check it, but I'm pretty confident that we didn't make a mistake there. X would equal 19. Just so you can see it here, just a slight wrinkle, tweak, whatever you want to call it, on this exact same problem. Just hear me out on this one. What makes this problem go from, hey, that was pretty easy, or like doable at least, like, hey, this plus this plus this plus this plus this equals 360. What turns that problem into, like, all of a sudden 90% of people are getting that wrong? That right there. Now, obviously, it stands out because I wrote it in pink, and it's like, oh, what the heck? But what's the mistake that everybody or a lot of people are going to make on this one? They're going to see, oh, I got some exterior angles. Sweet. Exterior. 62 plus 145 plus 69 plus 41 plus 58 plus 5x equals 360. What? No, wait, hold on now. So just confirm, make sure that you're working with you're working with all exterior angles. Where did that 145 come from? Going back to that concept that, hey, an interior and an exterior have to be supplementary. So, given the 145, I could go, okay, 180 minus 145. There's my 35. Now I could finish the problem the same way that we did earlier. So I just wanted us to at least hear and see, like, hey, there are potentially, things that make a problem more tough, or not necessarily a trick question, but just make sure that you're paying attention to some of that stuff. Okay. All right, last example. I think involving both interior and exterior angle measures, and actually our concept of regular. So it kind of pulls everything, I think, together in one problem. The base of a lamp is in the shape of a regular 15 gon. That's crazy. That's nuts. That's tough. I do have a tool here that allows me to draw. You see it highlighted there. It says, I thought it said it, regular polygons, which is kind of cool. It's without having to freehand it, I'm able to draw a 15 gon, so that's what the base of your lamp looks like. I'm going to take it off there because I know most people can't draw that, and I don't think you need to draw it on this one. But it's asking me for 2 questions, basically. A, find the measure of each interior angle, and B, the measure of each exterior angle. So the first thing to look at here, there's a couple of things. Obviously, regular hasn't come up in an example yet, but this word each, and I guess they go hand in hand, regular with each, we're able to find individual angle measures. Why? Because it's regular. Remember, regular means equiangular, so all the angles have to be the same. But this question's not asking me for the sum anymore. So just make sure, I know pretty much everything we did involved the word sum. Find the sum. The sum is this. Find the value using the sum, right? Whereas we're looking at one now, it's actually asking for specifically find each individual angle measure. All right. And we can really only do that because it's regular. So there's lots of different approaches here. There's kind of a long and a short way. I would say this: if you ever get the choice, or you're working with interior and exterior angle measures, I would always, and this is just a Mr. Kroll personal take, I would always start with the exterior angle. What? Why? I don't have to mess with the sum. Like right now, without calculating, do you know the sum of the interior angles of a 15 gon? I don't. I would have to calculate it. Not that it's a terribly hard calculation, but I don't know that off the top of my head. Whereas here, if I ask you that same question, do you know what the exterior angle sum of a 15 gon is? You say, oh yeah, 360. Never changes. So for me, starting with B is easier because I can take the sum of the exterior angles, which is automatically 360. And if I divide that equally among the 15 angles, right, a 15 gon has 15 angles, 15 sides, or I'm sorry, 15 interior angles and 15 exterior angles. If I take 360 and divide it by 15, which I still have to use my calculator. I just don't want to screw this up for the note purposes. 360 divided by 15 is 24. That's it. Like each one of my exterior angles is exactly 24 degrees. Why? Again, it's regular, so they all have to be the same. That's why I can do this here on this one. And then what I'm going to use is the fact that if I just make a sketch, a zoomed in sketch of, all right, that's one of my interior angles. We just figured out that we have a 24 degree exterior angle. So using the fact that these two together have to be a linear pair, if I go 180 minus 24, I get 156. So for part A, I know it doesn't give us a name for it, but would be a 156 degrees. So it's a good example of one looking at, where I've got an interior and an exterior kind of going on in the same question. It might not even be in the same question, but every time it's going to be easier to find an exterior angle measure versus an interior angle measure. So if you did it the other way, just so you can kind of see it, the sum of interiors, if you started here, you would have to calculate 15 minus 2, which is 13 times 180, which is 2340. And then I'd have to take that number and divide it by 15, which I hope, unless I screwed something up terribly, it works out. I get 156 degrees. So if I started there, fine, I got the same number. So I'm not saying you have to start with exterior, but I don't know, it's one less calculation that I have to do. I think the calculations were easier, 360 divided by 15, and then just 180 minus 24 versus whatever, some bigger numbers. In the end, I hope everyone's able to kind of follow there and figure it out one way or the other. And I think that's it. So let's take a look. I mean, obviously, I know we just had the one big goal for the day was find interior and exterior angle measures, find interior and exterior angle sums. So I think we've definitely hit them both. You'll see on the homework assignment that it kind of runs through a couple different situations, but I think everything that we covered and talked about in class, or on the notes. So yeah, we're good there. Let's check it off. Feels good. That's lesson 7.1 of the books. I'll see you in future lessons.